following conditions are satisfied. Generally, this is T is defined with V to U is just basic mapping between V to U. You feel that V is a one vector space. That means you feel it V is a one set and U is another set, you call it. Okay. I'll try to write on the board so that you can understand a little clear. Sorry. Some whiteboard I'm searching. Okay, I'm trying to find the whiteboard. I couldn't. Okay, see, V and U are the two vector spaces over the field F. The mapping is T is a function here. T stands for function here. The function is mapping between U to U is called as a linear mapping or linear transformation if the following conditions are true. Number one, first condition is vector addition. Number two, second condition is scalar multiplication. And number three, zero vector should be mapped with only zero. Zero vector should be mapped with zero. For any small v and w belongs to capital V, and T of V plus W is equal to T of V plus T of W. For any scalar k belongs to F, T of kV is equal to k into T of V. That means this T of V is the image of V in the vector space. T of W is the image of W in the vector space W. Okay. Now you should understand that V is mapped with the T of V indirectly. W is mapped with the T of W indirectly. This V and W are under the capital V vector space, and this T of V, T of W is under the capital U in the vector space. You feel that V is a one vector space which is defined two values V and W, and I am mapping this to the U vector U set, where U set, let me call it as a U1 and U2. V is mapped with U1, that U1 I call it as a T of V. W is mapped with U2, that I call it as a T of W. That means you are mapping U and W, you are mapping V and W of the vector space V in terms of their respective images of the T of V, T of W in the vector space U with the function T. Okay? With the function T. That image is represented by the respective function of the vector space V. That is a basic meaning here. Now, if you want to satisfy, if you want to say that this particular mapping this is basic mathematical mapping, functionalities, function or relation, whatever you can feel it. But if you want to say it is a linear mapping, that linear mapping should satisfy if and only if two conditions. The first condition is it should be satisfied with vector addition. The second condition is it has to satisfy with the scalar multiplication. The vector addition is nothing but the function of V plus W is equal to function of V plus function of W. You hope you understood what I mean to say. This T of V doesn't mean that what some function of V. It means that V in the vector space V is connected with the some other image in the U, their codomain is U, that is represented with the T of V. W is the sum of the element in the V or vector in the V. It is connected with the T of W in the U. Now, K is a some scalar. The scalar also belongs to the same field F. Then T of Kv is equal to Kt of E. If any mapping is satisfied these two conditions, then that particular mapping can be read it as a linear mapping or linear transformation, we say. This linear mapping plays a vital role in the place of vector space to identify the basic concepts or four concepts here. Number one, by satisfying the linear mapping, you can identify the null space of the vector space. You can identify the range of the vector space. You can identify the rank of the vector space. You can identify the nullity of the vector space. These are the four concepts identified through the basic principle of the linear mapping. Number one is called as a null space. Number two is called as a range. Number three is called as a rank. Number four is called as a what? We can say nullity. Null space is different. Nullity is different. Huh? Please be clear about the basic terminology of the vector spaces. With the help of this linear mapping, you are trying to identify the number one is called as a null space. That null space in future we call it as a kernel. Number two is called as a range. Number three is called as a rank. Number four is called as a nullity. These four are the principles are identifying of the given function t while satisfied these two conditions. Number one is representing vector addition. Number two is called as a scalar multiplication. If someone asks you, how do you define the linear mapping means, you should define that there are two vector spaces are defined over the same field F. Then mapping between these two vectors with the function t must be satisfied two conditions. Those are, number one is called as a vector addition, number two is called as a scalar multiplication. But that scalar multiplication also belongs to the same field, you should say. If this is the full-fledged definition of linear mapping between the two vector spaces over the field F. Okay? Now, these are the two conditions I told. One of the condition is T of V plus W, T of V plus T of W. Another condition is T of KV, K into T of V. If these two conditions sometimes is combined as, because of K is some scalar, no, the scalar can be defined some constant. So these two functions, these two properties, sometimes it can be combined as T of AV plus BW, we can say. Where A and B are the two constants. Small b and small w is also called it as a two vector spaces. Now, AB plus BW is nothing but A into T of A, B into T of W, where AB belongs to the same field, U and W are the same vector space. Now, this is combined condition. Above 2 can be represented like this also. Nothing is wrong. This satisfied whatever the statement we took now. This statement is satisfied both the conditions. Number one is called as a vector addition, it is satisfied, and parallelly scalar multiplication also satisfied. So this is a combined condition to say that T is called as a linear mapping. Hope you following my statements, all of you, my dear. Now, where A and B belongs to the same field, UVWV, and T of KB is equal to K into T of V. As you know, this is a scalar multiplication. If you assume that K is 0, where 0 is not a value here, you should feel 0 is a 0 vector. The 0 vector should be mapped with the 0 vector only. Please be clear. 0 vector should be mapped with the 0 vector. So T of 0 is equal to 0. What does it mean? Its image in the U is also 0. This K is equal to 0 representing on the vector space V. T of 0 is 0. Let us call 0 dash for our conveniences. This 0 dash is a codomain of T of V. That means 0 is mapped with the 0 dash Zero image is zero dash. Whenever a zero vector mapped with zero dash, then that is the reason zero vector must be maps to zero vector. It is also one of the conditions to satisfy the linear mapping. It is also one of the conditions only. Don't think that this is a separate case. It's not a separate case. It is one of the conditions. So you can understand now freely. There are three conditions need to be satisfied by any function to say linear mapping. Number one is called as a scalar vector addition. Number two is called as a scalar multiplication. Number three, zero vector should be mapped with zero only. If these three conditions are satisfied by any function, then that is called the linear transformation or linear mapping, we can say. This is the definition. I think all of you got my definition, my dear. Please read if you have any doubt here. Hope my screen is visible to all of you. You can read the terminology for understanding purpose. Okay. Yeah. Now let me go to the one problem to understand this context very clearly, all of you. You see here, the T is a some transformation is r cube to r cube. That means what? There are the three coordinates in the v vector space and domain vector space, and there are three coordinates in the codomain vector space. That is the meaning here. There are three coordinates. You feel x, y, z are the three coordinates in this domain, and the codomain is also possessing the three coordinates. That means T of x, T of y, T of z. A T of x is reflected with the x, T of y is reflected with y, and T of z is reflected with 0. That's the statement. T of x is reflected with x, T of y is reflected with y, and T of z is reflected with 0. What does it mean? I told you already. If I draw the two circles here, a V circle is possessing the three vectors x, y, z. This x, y, z is not elements here. X, y, z, you feel it as a vector only. A V vector is contained. You call it first letter in the transformation is V. You call it second letter in the transformation is U. The first letter transformation V is possessing three vectors, subvectors. I say these are called as subspaces. X, Y, Z. There are particular images in the T. This I need to maps no with respect to T. Function is T for us here. That is called as a translated. The translation of the P, T, V, the X translated. That means its respective image. Reflected image in the U is X only. The reflected image of the Y in the U is Y only. The reflected image of the Z in the U is 0. Got it? If I write mathematically, T of x is equal to x, T of y is equal to y, T of z is equal to 0. That is the meaning. That means I am doing mapping. You know there are three types of the mapping in the generally we consider as different types of mappings are there. Number one is called as a one-to-one mapping. Number two is called as a one-to-one mapping. One-to-one mapping can also be read it as injective. On-to-one can be read it as a subjective, and if any mapping satisfied with one-to-one and onto, then it is called as a bijective. Hope you clear about this. You have studied in the B level itself. One-to-one mapping, onto mapping, and bijective mapping. One-to-one is called as a subjective, what you call injective mapping. Onto-one is called as a subjective mapping. And both conditions, whenever mapping is satisfied with one-to-one and onto, then it is called as a bijective. Isn't it? These are the three mapping. Now here indirectly you are talking about the one-to-one mapping one. This is one-to-one mapping we can say. Now here again you have two terminologies. One is called as isomorphism, homomorphism. Isomorphism, homomorphism. Homomorphism means whenever mapping will be done with the same vector space, V to V, V and some vector space if we have, if it does the mapping with V itself, then it is called as a homomorphism. If you have a V vector mapping with some other vector U, then it is called as isomorphism. Homomorphism means within the same vector space. Isomorphism means two different vector spaces. It is indirectly isomorphism. Among that isomorphism and one-to-one mapping you are doing now. One-to-one mapping, face-to-face comparison. That means you are connecting face-to-face images. X image in the Y, X image in the Y. That is the reason I am telling R cube stands for the domain set is containing the three coordinates. Those three coordinates, three vectors I need to say, X, Y, Z. And codomain also possessing three vectors, X, Y, Z. The respective images you should understand T of X is equal to X, T of Y is equal to Y, T of Z is equal to 0. You want to verify your mapping whether it is linear mapping or not. As you know that if you want to say that any function is a linear mapping, it should be satisfied three conditions. So far I explained it. Number one is called as a vector addition, it should be satisfied. Number two is called as a scalar multiplication. Number three is called as a zero vector also should satisfy. If these three conditions are satisfied by linear transformation, then we call it as a given transformation is said to be a linear. Now let me verify one by one. You see, as I told you that vector addition means T of U plus V is equal to T of U plus T of V I should show, isn't it? Now let me define U is equal to some coordinates x1, y1, z1. This is, let me call it as a U. All of you please concentrate on the screen. Then easily you can understand very simple concept here. Don't make complicate the things, very simple. Just by observation only you can understand it. And UV is equal to x2, y2, z2. Both are belongs to the domain only. See, both are belongs to domain. Both are containing belongs to R cube. Why? There are the three vectors here. Okay, na? Now, let me write U plus V because the first condition is U plus V only. I should prove it now. So that you can ask why you took U plus V, sir. Why can't you take UV or U minus V or something else? Because of I need to prove that vector addition. That's the reason I added both the vectors U and V. If I took U plus V, x1 plus x2, y1 plus y2, z1 plus z2. I'm adding each coordinate with their respective. X1 plus x2, y1 plus y2, z1 plus z2 I did. Now let me take T of U plus V transformation, isn't it? I need to take the transformation T of U plus V. I took transformation for both the sides indirectly for sake of understanding you can feel. And T of x1 plus x2, y1 plus y2, z1 plus z2. Please try to concentrate here. You know that the transformation of T of x, y, z in the respect to another codomain vector space as x, y, 0 according to the problem. This is a transformation on codomain space, it is x, y, 0. Isn't it? Try to catch. X, y, z is codomain is x, y, 0. In place of x, y, z, what you have? x1 plus x2 you have, y1 plus y2 you have, z1 plus z2 you have. The transformation of x1 plus x2, the mapping of T of x1 plus x2 is, mapping of T of x is x itself. Try to catch the meaning of this statement. That's what I explained the problem initially itself before doing the solution. T of x is mapped with x itself. T of y is mapped with y itself. T of z is mapped with 0. That is their respective codomain, their images. Got it? Now, in place of x, what you have? x1 plus x2, as it is, I mapped. And T of y1 plus x2, I mapped it as y1 plus x2, y2. But T of z1 plus z2, according to this relation, it should be defined as a 0. So I took it as a 0. Understood? Why you can get it out now? Why sir took it's a 0 here? Please concentrate. In the place of z, if I connected the z with mapping, the respective codomain value is 0. Isn't it, my dear? Hope you catching my statement, all of you, please. Hope you catching my statement. T of x is x, T of y is y, T of z is 0. So that in place of z, whatever you have, it should be replaced in the mapping is 0. In the translation is 0. Okay, na? In the translation it is 0. It is projection is 0. It is mapped with 0. So x1 plus x2 as x1 plus x2 only. y1 plus y2 as y1 plus y2 only. The z1 plus z2 I mapped with 0. Clearer? Now I am separating these terms as two different vectors for my convenience. First x1, y1, 0, x2, y2, 0. This, for my conveniences, I have written like this. x1, y1, 0, x2, y2, 0. If I add this, will I get same or not? Certainly, isn't it? If I add this, definitely I get again original 1. x1 plus x2, y1 plus y2 plus 0, I get it. There is no doubt on that. This x1, y1, 0, is it not a translation of x1, y1, z2? Yes or no, my dear? This is C. x1, y1, z1, x1, y1, 0, is it not x1, y1, z1? That's the reason I written as T of x1, y1, z1. This now I gave you, this is equivalent to this now. In place of x1, in place of y1, in place of 0, z1 you have. That's the reason T of x1, y1, z1. x2, y2, 0, 0, I translated it x2, y2, z2, reverse translation. Codomain and reverse image it is. Okay, na? Now, this is indirectly U for U. It is indirectly V for U. So T of U, T of V. See, I took it as a U plus V. I proved as T of U plus T of V. First condition is satisfied. The first condition is scalar addition. Vector addition. Satisfied or not? If you have any doubt, you can ask me, my dear. Please, if you have any doubt, you can ask me. Don't hesitate to ask any doubt for everyone. Happily, you can ask. Come on. Any doubt, anybody? Hope you understood. Is it clear? Shall I proceed second condition? Yeah. Please respond. Majority are women only. Amma, please respond. Okay, thank you. I'm moving to the next condition. Our next condition is second condition is scalar multiplication. First condition is what? Vector addition. Second condition, scalar multiplication. T of k into u is equal to k T of u, isn't it? Where k is some scalar in the same field F. Let me call it let alpha. Alpha is some scalar. It is defined. It is also real number. Is defined in the same field F. It is a real number and also defined in the same field F. Okay, na? If I take alpha u, what is u? You took it as x1, y1, z1. Now alpha x1, this is some number, no? Alpha is some small real number. That real number, I am multiplying with their respective vectors x1, y1, z1. So that alpha x1, alpha y1, alpha z. Okay, na? Now I call it alpha u is equal to alpha x1, alpha y1, alpha z1, I can say. Alpha x1, alpha y1, alpha z1, you see. Now let us take the translation of that. Let us take the translation. I mean to say codomain. Take t on both the sides. Take t. That means I am keeping the mapping function. The function means what inside indirectly translated. A translation. That means you are trying to identify the projection of that value. Isn't it? You are identifying the projection of the value. That projection we want to take in terms of the transformation. So T of alpha u, let me call it. I took it as a T of alpha u. You know that alpha is some scalar, u is a vector. Now I need to be translation. That means I need to project it. So take T on both the sides mathematically, simply speaking as a mathematical language. T of alpha x1, T of alpha y1, T of alpha z1. Again go to the question. T of x by z is equal to 0, x by 0. which means that in place of x in this new transformation, you have alpha x1. In the place of y, you have alpha y1. In the place of z, alpha z1. Isn't it? The alpha x1, the function is alpha x1 itself. Alpha y1 codomain is alpha y1 itself. But alpha z1 codomain is 0. Why 0? According to our translation, it is a 0. Projection mapping, it is a 0. In place of z, it should be mapped with 0. That's the reason it is 0. Now, what is common here? Alpha is common. I took it x1 y1 0. Is x1 y1 0, isn't it? T of u or not? Yes or no, my dear? X1 y1 z1 0, no? It is T of u. So T of alpha u is equal to alpha into T of u. You see, second condition is also satisfied. Isn't it? Second condition is also satisfied, you see. So scalar multiplication also satisfied. Already we proved vector addition is satisfied. Now we proved scalar multiplication is also satisfied. Third condition I told you, null vector. Let us define x, y, z are 0, 0, 0. Okay, na? Let us define x, y, z are what? 0, 0, 0. Now null vector 0 is equal to 0, 0, 0. And T of 0, translation, the translated image, the projection image. X replaced with 0 now, 0, 0 only. Y replaced with 0, 0 only. Z anyhow 0 in the original question itself. So T of 0, 0, 0. That means 0 vector you mapped with 0. So null space, null vector is mapped with null vector. So three conditions are satisfied. Got it? Three conditions are satisfied. That's the reason the given transformation T of R cube to R cube, triplet, it is triplet indirectly. R cube to R cube is called as a linear mapping. Please go through the example once again. If you have any doubt, free to ask me. See? Clear? Question number 1 is clear. Question number 2, you see. Now, let T is a mapping between R square to R square. That means what? Domain containing two vectors, x, y. Codomain containing two vectors only. Their images also. Okay, now their images also containing two only. So R square to R square, translation. I told now using translation defined by T of x comma y is equal to x plus 1 y plus 2. Show that it is not linear transformation. Previously your question is what? Show that it is a linear transformation. Now you are showing that it's not a linear transformation. See now. Now it's not a linear transformation means you have to prove that one of the conditions are not satisfied. Among these three, any one of the condition is not satisfied, you say that it is not a linear transformation. Among these three, any one of the condition is not satisfied, we call it as a not a linear transformation. First, I am trying to verify with the null vector satisfied with the null vector or not. Okay, na? Null vector, whether it is satisfied with the null vector or not. Indirectly, I took it as a u is equal to x comma y. U is a subset of the domain set. It is a subspace of the domain V. Okay, na? Now I consider x and y are 0, comma 0. So the 0 vector is 0, comma 0. Their translation is what? T of 0 is equal to T of 0, comma 0. Please catch the statement. T of 0, comma 0. T of x plus y image is what in the codomain x plus 1, y plus 2. X and y are there in the V vector space. X plus 1 and y plus 2 is there in the U vector space. I mapped x with x plus 1. I mapped y with y plus 2. Isn't it the meaning of this statement, my dear? With the reference to t, I mapped x with x plus 1. I mapped y with y plus 2. Isn't it? Now I took it as x and y are 0, 0. If I take x and y are 0, 0, by replacing x by 0 and y by 0, what is its image, my dear? 1, 2, no? But indirectly you are telling that 0 vector is not mapped with 0 vector. Isn't it? Originally you took it as a 0 vector in the domain, but in the codomain it's not a 0, it is some other number, it is mapped. You are mapped with some scalar. Though it is in the same field, but it should be mapped with 0. That is a condition as far as a statement of the linear transformation. But you map it with 0. That's the reason. You map it with some number. So 0 vector is mapped with some number so that it is not a linear transformation. Isn't it? Please go through it. Okay. Hope you understood this. Why it is not a linear transformation? Because of it is not connected with, it's not mapped with the null vector. So it is not a linear transformation. Next meeting, I will continue these two top problems. Two more problems I have with me. I'll continue this. Thank you. My request is someone take a lead to share the attendance to the madam only, or you keep that in the group. Okay, ma? Have you got my statement? Please keep the attendance in the group. Okay, thank you. We'll continue in the next meeting. I'm closing the session.